Okay, so the last time we were giving some order theoretic view of the entailment relation, let's call it like that. We wrote A less than or B to mean this thing, and we started investigating what properties we have for this order. So first of all, we need some names for properties, and we know, or we introduced, I don't remember, like what it means to be a top or a bottom, easy things, like top means you are above everything else, bottom means you are below everything else, and some interesting binary notions were to be a meet and to be a join. Where's the join? To be a join. So let's remember this. Meet means that among all, first of all, you are a lower bound, and among all, okay, it's a binary notion, so it's not just a meet, like top and bottom is just a top and just a bottom. It's meet of two given things. So the meet of A and B, first of all, it's a lower bound of A and B, so it's below A and it's below B. And secondly, it's the best among those things, and here best means that if I have another thing that is also a lower bound, manages to be below A and below B, I call this C because it's my candidate. The meet is better than the candidate. Here, better means greater. Okay, better does not always mean greater. We saw that last time. Sometimes means least with this property, as is the case for the join. We have met meets and joins, like probably if you've taken calculus, meets are the infima and joins are the suprema. But when you meet this in the real numbers, I don't think it's the best setting to meet this for the first time because the order is too nice or too ugly. It depends on how you look at it. The reals look like that. So whenever you have like two numbers, it doesn't really make sense to investigate the concept of join and meet because the join will be the maximum of these two numbers and the meet will be the minimum. It's a total order, right? Every two things there are comparable. So joins and meets are always one of the two things that you give them. While if you take a more interesting order, like the one we saw with the integers and the divides, we saw like something like this. We were looking at common divisors, and so this is not the whole picture of the integers, like it's just a subset of the integers that it's interesting to, if I'm looking for the common divisors of 12 and 18, and remember that here there are implicit plus or minus in all of these things. So like if I'm looking at 2 and 3, and I ask what is their join, it would be on all upper bounds of 2 and 3, and here's the first quiz question. What are the upper bounds of 2 and 3? Which members satisfy this? Yes, Rafael? 6, 12, and 18. And you agree, right? Okay. So, did you answer investigating what the order means or looking at the drawing?
At the drawing, but...
No, this is the correct thing. Okay, this is what I wanted. Okay, so if you look like at 2, all the upper bounds of 2 are 2 itself are like these things here. And of 3, all the upper bounds are like this thing here. So the common upper bounds are these guys, right? So it happens for 12 and 18 that if I look at, for 2 and 3, that if I look at the upper bounds, the common upper bounds, there is a list 1. Yes, there is a list 1. So this will be the best upper bound. This is the join of 2 and 3. Similarly, if I ask for the meet of 4 and 6, the answer should be 2, right? So you have this visual representation, and if I look at the common divisors of 12 and 18, which is just this little subset here, it happens that it has someone that dominates the whole set. So it does have a greatest element. Again, when I say greatest, I don't mean with this order. I mean with this order. This order is irrelevant when I'm doing number theory in this sense. Okay, so imagine now that we are trying to calculate 12 and 18, the greatest common divisor, like it's an introductory number theory course, and like someone was late, as I hope that some people will be late today. And we're investigating this, and eventually we have come to state all the divisors of 12, which are these, and all the divisors of 18, which are these, and we have found the common divisors, which are these. So imagine that at this point somebody enters the room, right? Okay, I'll fix this a bit. So forget about this right now. So we have realized that the common divisors are these guys. And since it's like we've been talking about for like 5 minutes, we don't repeat every time the common divisor of 12 and 18. It's just, okay, we found the common divisors, it's these guys, and the question is, what is the greatest common divisor? And my point is that the person who just entered now can still answer without knowing what were the original two numbers we were looking for. Maybe it was 12 and 18, maybe it was something else. But the moment you have the set of the common divisors, you realize that as a subset of the whole picture of the integers, it's still an ordered set. It has a picture, you can depict it, and you can look at it and decide what is, if it has a greatest element, the top, and you know, okay, here's the top element, it dominates, this is a greatest common divisor. I don't know what you were looking for, but I know that the greatest common divisor is 6. It would not be the case if when they came here, imagine I had picked some different 12 and some different 18, and the picture was like that. So the student who just arrived, not you, is wondering like what two numbers are. But okay, the classmates did some work and found out that the common divisors are these. Okay. Now, if you confuse yourself and you think that the greatest in the word greatest common divisor is related to this order, you will say, I know the answer, right? Because if you compare these things with a different order, and remember again, I'm emphasizing this is actually plus or minus everywhere. You will say the greatest common divisor is what? Help me, yes? 6, yes, but you would be wrong. Because this is the order that matters here. So in this case, you will say, you should say what?
Simply neck.
The what?
Simply neck.
No, because look, it's not that Areti forgot 6. Okay, first of all, in a sense, yes, because Areti only said plus 6 because he's looking, let's say, at that, because that's what I asked. Here you say, okay, minus 6 is also like a greatest thing, but none of them, neither plus 6 nor minus 6, manages to dominate 4. Right? Because 4 does not divide either of them, neither minus 4. So all these guys, in a sense, are some like upper bounds, but no, I cannot say greatest because this did not dominate this thing and did not dominate this thing as well. And this, even though dominated all this part, it didn't dominate this. So in this sense, when the students comes in, you say, okay, so they picked two integers in which the common divisors don't have a greatest element, and greatest means greatest with this. And now maybe Arete has this face because, say it. Okay, you still have hopes. No, 2 is still not a greatest common divisor because it doesn't dominate 4 and does not dominate 6. Okay, so what's going on? It's like a theorem of number theory, which does not concern us here, that no matter which numbers you pick, if you look at the common divisors, this situation will never happen. It will always look something like that. There will always be a greatest element, with this order, a greatest element of your common divisor. So if you step in a classroom looking for two integers and it looks like that, somebody somewhere has made a mistake or trying to make a point like I'm trying to make a point right here, okay? So, but this is a theorem of number theory that does not concern us right now. It's the existence of greatest common divisors, okay? And similarly for meets, I think for meets, no, these are the meets. Similarly for joins, with some of you, I don't remember who, realize that the joins are,
LCM.
yes, the least common multiple. Yes. And again, I will want to visualize the word list here again as best. Okay. It doesn't make sense to take the greatest common multiple because the greatest common multiple is always what? Which one? We are interested in the least common multiple. Ο ελάχιστος. Come? Ελάχιστο κοινό πολλαπλάσιο, yes. It would be uninteresting to consider the best common multiple to be like the biggest, because which one is the greatest common multiple? 0. Yes. So I think it was you that realized, maybe I'm not sure, how the picture of the integers looks. You have the bottom, which is 1, top, it's 0. What is the first floor? Okay, come on, let's... Okay, what are the... Don't worry about it. What is the first floor? No, let's say this is floor 0. Yeah, so here we have the primes. Interesting, okay, the next floor would be like products of primes, but including like 3 squared, but not 12, right? Because 12 has like 3. Okay, so you understand how these things go on, and I hope you realize that there is no penultimate floor. Whichever number you may think enter in this penultimate floor, you can always find like multiplied by your favorite prime, and you will find someone who is strictly between your guy and 0. Okay, so enough with this design, I think. And any questions? I'm still in the idea of talking about joins and meets and a bit of like order theoretic stuff. Okay, so since we have not studied posets or prosets, I will say a few things about this, and I will make, okay, this is not very common, but I will try to study them at once. Usually you see them as posets, and poset means partially ordered set. I cannot write it right here. Okay. I'll figure it out. Okay. So this means like, so if you take poset, it's like partially ordered set. While if I add the R, it's like proset, it's like a set with a pre-ordered. It's a pre-ordered set. So what is this thing? I will write it like that. Similar with what we do in group theory, I will say it's a calligraphic P, it's a fancy P, which has a normal P, which you can think of it as like a set or a type, or what have you, it doesn't matter. We will call this thing like the carrier of the, exactly like we do in group theory. So this is the carrier set, or the carrier type, if you like. And this is equipped with a relation, which we usually write like that. And this has to satisfy 2 things. And I think we have mentioned which these 2 things are. So this is reflexive, and it is transitive. And if I'm here, so far, if I have this is a pre-order. And if I also have antisymmetry, then I have just an order, or some people say partial order. Like, okay. One of those people that might even call just an order, even if it's a pre-order. It was an exercise, and Manolis promised to write this on Zuli, but he didn't, to show how to justify the name. Like, why is it called pre-order? It indicates something, and in this case, it's a fair name, but we need to verify it. And I will just state the objective of this exercise is like, if you have a pre-order P, find a way to associate with it P in such a way that this will be a partial order. And of course, when I say find a way to associate with it, it doesn't mean, there would be, if I stop like that, and you want to troll me or something, you can say, okay, give me any pre-order, and I will give you back, like, the real numbers with this thing. This is indeed a partial order, and I will send every pre-order to this one. Obviously, this is not a nice answer. Somehow, the order here has to come in an essential way through this order here. Has to consult or be based on, or whatever that means. This is part of the exercise. So this is what it means to justify a name, and I will give you, I don't think this is the first time. Is it the first time a homework is like justify the name? Maybe it is. It is? Yes, okay, so we'll see this again. For example, like a very bad name is like pseudometric. If you have seen this in metric spaces, it should be called pre-metric for the same reasons. Like it's something you can get a metric out of it if you do some work. And in this same sense also somebody could say that why pre-order? Because if I see only these two, okay, if I see these two and you add this one, I understand I go to an order, a direction order. But if I see these two, these are also the same two components of a different interesting kind of relations, which is? Okay, so if you have a relation, forget the symbol, because even the symbol I'm using is indicating that I'm thinking things like I like orders. Okay, use a generic symbol like R, or I don't know, let's call it R. So if you know that this relation is reflexive, and if you know that it's transitive, and if you like orders, like partial orders, you may think, I would like to also have antisymmetry, and in this case, this thing becomes an order. So if you give me something that is only these two, a pre-order, I consider it in fact a pre-order because soon I will want it to become an order. But there is also a different class of relations, interesting relations, binary relations, that also have these two properties. But in what sense? The idea is that no, wait. Forget propositions and logic. Everything we do has to do with proposition and logic. But right now we are looking at an abstract way of orders. So I don't have logic yet here, right? I have a relation. Okay, let's remember what a relation means. A relation type alpha is just a synonym for this thing. Alpha cross alpha to prop. For example, divides is a relation on the integers, less than or equal to is a relation on the integers, is a subset of is a relation on a power set of some set, is a mother of is a relation on humans, and stuff like that. So if you see consider a relation that has this property, what is the third property you expect to see? If it's this one, you like orders. If it's a different one, and I'd like to see which one, yes? Symmetry, you like equivalence relations, right? Okay. So in a sense, this could also be called a pre-equivalence relation, but okay, let's stick to the name it has. It's a pre-order. And when I say I have a poset, it means I have this. And when I say I have a proset, it means I have this. Okay? So these are like nice mathematical objects, structures. They are not, at least superficially, they don't seem to be algebraic, because remember, algebra means, first problem to call this algebraic is that this thing is not an operation, it's a relation. So we're already outside the door, even from the very old school algebraists. And secondly, the axioms that I have, the laws that I have are not equations. They're like for all and implications and whatever. So it's not, it definitely does not look algebraic. Any questions? Okay, so this is like order theory. Order theory studies these kinds of objects, sets, and you should always have a question when somebody introduces supposedly a new mathematical world, a new theory, and just told you what the objects we are going to study are, because I'm pretty sure you understood what the objects are. They are sets with an order, and even you even know how to design these orders. Like I could tell you, okay, let's consider this order. You know which order I'm talking about. Like it has two things like that. They are orders like this. This is supposed to be a straight line. Or let's consider this order and ask questions about it. Like, does it have a top? Somebody? This one? Wait, these are two different orders. So first this one, does it have a top? Which one is it? The one at the top, right? Okay, so, yes, so this is the top and we denote it like that, usually. Does it have a bottom? Yes, it's the one at the bottom. Same question on the right, does it have a top? No? Okay. Does it have a bottom? Yes. Okay. And we have one more thing. Does it have joins and does it have meets? And we will enrich our vocabulary. But the idea is when I say does it have joins, I have to say like binary joins. So does this have binary joins? What does it mean to have binary joins? It means that if I give you any two thingies here, there is someone that satisfies what it needs to satisfy to be the join of this, to be the greatest the lowest upper bound. I always want to say best, the best upper bound. So are joins guaranteed here? When I ask if a poset has joins, it's not enough to say, take this one and there is a join of these guys. It would be as if in the integers you found that 8 and 6 have a greatest common divisor, but some other numbers may not have common divisors. So if I say, here in this poset, we have joins, we have binary joins. It means that any pair of inhabitants of this world, the world guarantees that there is a join for these two. So let's look at this world here. Are there joins? Yes, okay, you can, we said yes, right? Okay, you can do that, like, take all there are not many, like 4 cases. Like top with top would be join. The only interesting one is if you take these two and the join would be this guy. Similarly, it has meets. And here it's like, does it have joins? No, because even though it has a join for these two guys, it's this one. If I pick these guys, obviously there is no join because, let's see, in how many ways can something fail to have joins? Remember, join means the best of the upper bounds. Either you have no upper bounds, which is the case here. So if you take this one, what is the set of the upper bounds? Yes? No, because to be an upper bound, you have to dominate all the set. Yes, so there are no upper bounds. And therefore, there is no best upper bound. So one of the reasons you can fail to be a join, to have a join, is because there are no upper bounds. And the other reason is there are upper bounds, but there is no best one. Okay? So let's try to depict this like I could have it like that. Now, if I'm not mistaken, if I ask for the joins of these, it's the other problem. What are the upper bounds of these two? All these. Hope you agree. Okay. And now, if I thought that best upper bound means the top, the highest, I would say, it has a best upper bound. No way. Okay. The best upper bound is the one that's closest to dominating everyone, lowest, let's say. So we have the other problem here. It has upper bounds, but it doesn't have a best upper bound. It does have a biggest, but nobody cares about biggest upper bounds. We care about biggest lower bounds, okay? So this is a different reason why something can fail to have a join. Okay, makes sense? Okay. If I only have like these two notions here, okay, sorry, I was saying this. When I asked you if you have any questions so far about the thing we are studying, you said no. So you should always have the following question. When someone introduces a new mathematical theory, like objects of study of interest that we want to study, like a new world, the world of posets. Okay, let's see what's going on. And I told you what posets are. And you may understand, okay, I know what this world looks like because this guy told me what poset means, so I can visualize the posets. So you should always ask, what is the way that gets me from one object to the other object? And if I don't determine this, I have only, if you tell me that you're studying these objects and you don't tell me how to get from one object to another, I don't know in which world you are living. It's like you gave me a map of islands, and there are no, I don't know the routes of the planes or the ship. I don't know. I think you get the idea. So I need to say something more in order for you to understand what we're studying. And this is, I need to tell you how we get from one poset to the other. This happens in group theory, and when you first study group theory, and unfortunately you think that you study group theory even after the first class, and usually people are too late to say how we go from one group to the other. What is the notion of transportation among groups? Yes, but you don't hear the word homomorphism in the first class, right? When you study, you take a group theory course. I mean, maybe you do, I don't know. But usually it's like a bit later. And I'm trying to argue here that until you hear the word until you have an answer of how you go to one group, from one group to the other, you have no idea what world this is. Because this is part of what the world is. If I tell you, actually I want to study group theory, but I want to only consider monomorphisms, this is a different world I'm studying. Okay, so I owe right now to tell you how we go from an ordered set to an ordered set. And I'd like suggestions. And the suggestions can come from what you've studied in even group theory. Usually, not always, and this is a big point. Usually, if your objects look like sets, and these things look like sets, they seem more like sets. If you look inside the poset, you see something like that, right? Okay, so there are some sets involved. Usually the way to go from one to the other is some kind of function, but not completely arbitrary. It's a function that plays well with the thing that interests you, which is supposedly this relation here. Yes, Sarah, do you have a suggestion? Yes, or a question? Wait, because, okay, first of all, what it means, what I'm asking means this. I have this guy here, and I have this guy here. Let's call it a fancy Q. This is supposed to be a fancy Q. And the question is what does it mean? What should be acceptable as a weight that will get me from fancy P to fancy Q? Yes?
Should it go from the bottom, from all the list elements and pair them one to one and then sticks at the end whatever remains?
Okay, you are somehow, for some reason, emphasizing the list element, but you said the lists, you said plural.
A list, exhaustively to be moving from the smaller, the least element. Exactly.
Okay, so it's, what ways would you have here? In this example that I have here, what would you suggest to be something that can get me from this poset to that poset? It should be a function that has some properties. Let's start with this.
The bottom to the bottom.
No, before that. So it's a function from this set to this set that takes care of some things. So so Sotir says I would like to get the bottom to the bottom,
yes,
and probably the top to the top.
No.
No? Whoa.
The top would go to. It has to go to any of the next layers.
Okay, so you're emphasizing a very specific construction. So you have already two ways of getting from here. One that selected this as a top, and a different one that selected this as a top.
Exactly.
Right? So one looks like this, and the other looks like this.
Yes.
Okay? And for some reason you're emphasizing the bottom, but some Manolis might say, why not start from top and maybe take this one and this one? I mean, I don't think we can argue. Okay, maybe I defined the bottom first, I don't remember. But they are equally important concepts if they exist. But
it feels that if I am able to compare two elements on the set on the left, that after function transformation, the same comparison should be holding on the right. That's why
I didn't like the word function transformation. You mean after applying the function?
Yes, that the pre-images and the images, that they satisfy the same inequality. The same.
Okay, but look, The thing is, for some reason, you are giving importance to bottom. And you would be absolutely right if bottom was here. Like if it was one of the, let's say, protagonists, I will use this word again, of what an order partial poset is, you would say, okay, it has to respect this thing. But okay, look, this is a poset as well. And it has no bottom. Maybe you can say, yeah, so I don't want any way to reach this thing. I don't want to reach this thing from anywhere because it doesn't have a bottom. But the point of view here is to forget that bottom has a significance. Maybe, in case there are bottoms, they will end up being respected. But the thing that should be respected here really is just what is there as a protagonist of the poset. In this case, is the order.
Yes, what I meant is bottom just happened by accident to be the least element on the set on the left. But I would just say that the smallest element you can take should go to the smallest element. And you should move exhaustively because
what if there are no smallest elements?
Then you can do whatever you want. You have no constraint that you need to satisfy.
Okay, different suggestions? Yes?
We have a function.
Okay, everybody should think like it's a function that does something.
Yes,
The question is, what is this something?
I would say that respects reflexivity, transitivity and antisymmetry.
Okay.
Και έχω και μια ερώτηση εδώ πέρα. Γιατί στο καλλιγραφικό δεν βάζουμε μέσα το transitivity, το reflexivity σαν πρωταγωνιστές, σαν σχέσεις?
Okay.
Όπως για τα groups, ας πούμε.
Okay, good question. We didn't do this in groups yet. I mean, I gave a spoiler.
Inverse function.
Okay. Let me go back to this. When I was studying groups, I think I only gave a spoiler. We did not do that, I'm pretty sure. I said, first of all, we should realize what the real protagonists are, and there are three, okay? So it's like this, and some inverse here, or whatever. And I think we stopped here. And I gave as a spoiler that later on, when we fully appreciate what proof relevance and the type theory has to offer here, the next things, like the axioms that I want, the equations that I want, will end up being like extra things here, which are like 5 equations. You have associativity, 2 for the identities and 2 for the... Did we do that here? I mean, have we seen group as not a 4? I thought when I said the group here, usually it was a 4 things, but actually it can end up being 9 things if the next 5 are the axioms. In case you do that, in case you see it like that, here you have to add these 3 things if it's a poset, or the first 2 things if it's a proset, okay? But you said something else that I want to pick a fight with. You said like respect reflexivity. These things are not really things you respect in this sense, for the same reason that when you have an homomorphism, it needs to respect the operation. It doesn't need to respect the group laws. Like the 2 things on the left and the right are groups, in this, or here they are posets, so they respect their corresponding relations, have all these properties. What you take care to respect or to preserve are operations and relations when they are there. So let's, but what you said, like, you're getting closer. You need to respect.
The 3 reflexivity, transitivity, and antisymmetry.
That's exactly, that was exactly your first answer. And I'm trying to tell you that it doesn't make sense to say, I want to respect. What it would mean to respect reflexivity?
Yeah.
You are from one world that reflexivity holds, and you end up in another world that you already know that reflexivity holds, right? So you take a function from here to there, it doesn't make sense to sense that, to say that f will respect reflexivity, but it makes sense to say that f will respect the relation. So we're reaching the answer here. So where was my beautiful design here? Okay. So what does it mean to have a way to go from calligraphic P to calligraphic Q? Okay, from the poset, it means that f. I will use the word preserves. You also see respects, but I prefer to use respects on operation. Preserves this one, and what does that mean? Can somebody guess? Only one. Yeah, 2. Okay, Manolis. Yes, go ahead.
So I'm not 100% sure. I have 2 possibilities. Like one One is that
First of all, which letter is implied here? Preserve, the left or the right? Because technically, technically there are like this one I have a subscript P, and this one have a subscript Q.
I think that ties into my question. Like, if we have x is smaller than y, then phi of x should be smaller than phi of y, but should the opposite also hold?
Okay, perfect. Okay, so the one we are interested in is the one you said. Like, okay, so it's this one. Preserve this means the following, that as soon as I have like this in P, then I can infer this.
I think I'm starting to get what you were saying about homomorphisms and stuff, less homomorphisms.
Okay.
That's really annoying.
Okay, I think it's satisfying. The thing is annoying. What was annoying for me was like a feeling that I've been told lies like all my life. But okay, we'll go back to that because we don't have the idea of monomorphisms yet. What we have that starts with mono is monotonicity, and this is like sometimes called we say that phi is monotone. Okay, it's like this is what is this what you know as monotone functions? Yes, okay, of course. Just trying to see if you pay attention. Okay, classic excuse. Yes, it's a Q there. And actually, why do I make this mistake with P and Q? Because like as soon as we mature level 0.1 in orders, we don't even mention that for the same reason that when you're doing group theory, maybe when you start talking about homomorphisms, you say something like phi of x, and there you have a g or an a, I don't know what your group is, y, and you say that this must be equal to phi of x operation phi of y, and maybe the first time you do that, you are writing the subscripts, but like you realize that it's useless because you can infer the correct types here, even if you don't call it like types or type inference. If I remove this, you know that this operation is is the operation of A because X and Y live in A, and you know that's the operation of B because you have transported X and Y to the other side, B, and so this can only be the operation of B. And for the same reason, I can write this, okay? But since this was the first time I'm writing, I made a mistake, okay, thank you. And now I can like get away with it and not writing anything because you know which relation is from the context, okay? So sometimes, okay, a different name for this is like isotone. Because sometimes in text, especially analysis, you have like, you call monotone things that are increasing, but also things that are decreasing. So the decreasing ones do not respect the order. They do the exact opposite. They say like, if you have something like that, if this thing implies this thing, I don't know if you prefer to see it like that, or if you prefer to see it like that, okay? But sometimes you call monotone a function that can have either of these, satisfy either of these properties, okay? You've seen that, like, calculus, is this monotone? Okay, with my first definition it is not. Okay, but if you want to never fight with anyone about whether it is monotone or it's not monotone, because think about it, this does not preserve the relation, it flips it, right? So if you want to make sure that everybody will understand what you say isotone for it goes the same way, it keeps it the way it is, and antitone if it's like that, the thing I designed. So this thing is antitone, and this thing is like isotone.
I think we would call them either increasing or non-decreasing.
Yes, it has this name as well, like non-decreasing. This is very, very weird, very negative, but it's okay. So we now know what the arrows are. Let's say the arrows, I mean the ways that transport me from one to the other. Manuel said, what about the other way around? Should they have more obligations? The answer is no. I want to be interested in this thing. If I do stuff like that, it means like I'm restricting the means of transportation, which is the equivalent to saying group theory, I want to see only monomorphisms. I can do it, but it's a different world. If you tell me that I can only get from a poset to another poset if I have these extra properties, I will lose some of the arrows, some of the transportations. In the same sense that if you study group theory and I take away of you all homomorphisms that are not monomorphisms, it's a different world. There were some groups that you could go to, but you cannot go anymore, let's say.
I think this, the thing that's tripping me out is that in group theory, for example, this is kind of automatic because, like, I mean, I think it's because of equality for some reason. Like, equality kind of ensures that.
In group theory, you would never have this question that you have, should I do that or not, because you only have, you need to respect the operation. There is no sense in asking if the operation is respected the other way. It doesn't really make sense. While here, it makes sense, and when this happens, we say reflects. So I will write this definition, because we might need it. We say that phi reflects, but be careful now, it's the other one. And this means, I think you guessed it, that if you have, like, for any x and y, if you have that phi of x, help me here, q, phi of y, then you can infer, it's this one, okay? I think it's better if I write it like that. It's this one. This would be like reflects, this is preserves. This one. And this is reflects this one. But again, my official definition of what the transportation means are between posets is monotone or isotone, to not confuse anyone, function. But in the neighborhoods of order theory, we always call them monotone, so I will say it monotone as naturally as well. We'll stop here for like a 12-minute break, and we come back. Yes.
Το δεύτερο, το reflex, το χρειαζόμαστε επειδή είναι μερική διάταξη.
We don't need this one. Forget about it. It's like I just mentioned the word because I might use it. It's like in monomorphism in group theory, you learn that this thing exists, but it's not like it's a requirement for a means of transportation from a poset to another. The only thing you want is that it preserves the order. It doesn't need to reflect it. And you can say, okay, I want to study what happens in case my function also reflects the order. I'll get some extra stuff in the same way that in group theory, when your function happens to be like injective or surjective, you get some extra like theorems or something like that. Okay, so after this definition, I know what you're talking about because I know what the objects of interest are, which are like posets, and I know how you go from one to the other. Now, if you tell me, like Sotiris seems to like this bottom thing, and it makes sense to like it, you come like with a different kind of structure, that you say something like, okay, I want to consider some structure like this. It has, so far it's a poset, and there's another protagonist, it has a bottom element. And if I say it like that, it means that it satisfies all three things that you, or maybe proset. I don't know if you like antisymmetry or not, but let's say you like it. So these things will say that P is a poset. And obviously, since I added a new protagonist in the signature of what I'm studying, of my structure, probably I will want to stipulate something about it, and probably I will want to stipulate this. That for any x, bottom is a bottom. This thing is really a bottom. If I do that, it means that now, if I want to consider means of transportation from things of this type to things of that type, so now I'm not studying posets anymore, I'm studying posets a la Sotiris. Posets that Sotiris likes. And this is very valid, and this is an important class of posets. So, in this case, if I ask you, wait a minute, you have not defined the means of transportation, the obvious thing to do is, first of all, okay, it will be a function from the carrier set of the first to the carrier set. Sometimes the carrier sets, we denote them like that. Okay, so it's a function from this to that, such that it preserves this. Okay, so it's the same thing we had, but since I have another protagonist here, I have to respect this thing as well. Pretty much, and every time you have a mathematical structure and you want to worry like what is the default, the standard way to go from one structure to another of the same kind, it's like it's a function that respects everything there is to respect. So here it must preserve this, and now it has the obligation to send the bottom of the P to the bottom of the Q. And if for some reason you like bounded posets, which means that besides bottom they have a top, and this means you have another law here, then you will also require your functions you have to send the top to the top. So back in my example, with if I see them as posets, it means that I have a lot of liberty here. I can say, I can map this thing here, and this thing, let's say also here. This preserves the order, right? It didn't break it. It didn't send top to the top, bottom to the bottom, but as far as I'm concerned, I don't care about tops and bottoms, so no reason to do that. Now, if I take another way I could place this inside here, it would be like taking the top here and maybe the bottom here. What I could not do is like take the bottom here, the top here, and the bottom, for example, here. Because I did not preserve the order. This was less than to that, and now they are not. Okay? Don't think just that they're flipped. It would be equally bad if I put this here and this here. They used to be comparable with bottom being less than top. Their images are not in the same configuration. I don't care if it's because they are not comparable or if it's because they swapped places. Okay? Make sense? Okay. So if you like top and bottom, you only have one means of transportation to going from this poset to this. Now that you care about top and bottom, because you are forced to send this one here and this one there, and you don't have any other choice. While the Soterian posets need to put this here, and this guy can be anywhere they like. Even here. You can send it here, it's respected. You can send it to the top, you can send it anywhere else. It's a means of transportation. Does that make sense? Okay, and same thing for joins and meets. I could say that, okay, I won't be interested in posets that satisfy, that guarantee, binary joins and binary meets. And this means that in my signature here, where was it? In my signature, I have to add more things. Now I have this order, and I want to guarantee that I have a join and binary meets, and maybe I stop here. And Sotiris likes this and said, no, but wait, I want top and bottom as well. A different thing. So depending on what I will put here, what the actual transportation will change meaning. Be careful, these things, the binary ones, and this as well, the zeroary ones, are operations. And this thing is a relation. So the way I'm writing this, I still don't have the right to say that I'm doing algebra. It has a relation that satisfies some things that are not equations and has some operations. And about these, and probably about these, I don't have an immediate way to see an equation out of them. So far, nothing I'm doing seems algebraic. Now, if you look at posets and you want to restrict your attention to posets that have certain nice properties, like, for example, they have a bottom, or, for example, they guarantee binary joins, or they guarantee binary meets, or they guarantee all of these things. Let's put it like that. I will call it an L for mysterious reasons, and I will say, okay, let's consider this thing that has like and guarantees somehow joins, meets bottom and top. And you know what joins, meets, bottom and top mean order theoretically. But this means like every time that you can send like a pair of A and B, you can set it to a unique thing, you have an operation. So in order to do that, I have to prove a certain thing. I have to prove that binary joins in a poset are unique. And this is very easy to prove. I don't want to do it, but essentially what you do, since you are in a poset, you pretty much say that consider any other join, each will be less than or equal to the other, and from antisymmetry I get that they're equal. And this means that I can define an operation. And this means that I can see if I'm like flirting with the idea of transforming this and looking at this completely in an algebraic way. And this means that I will not have this, and all my things will be equations and for two operations. And the idea is what kind of, the question to ask is what kind of laws, how can I express these laws in terms of equations? So I want a way to translate the idea of something being less than or something to a join. Now, if I look at what A less than B means, somehow it means that they are comparable and there is a way of growing from A to B. If I have a finite hash set that I can look at, can somebody guess what this is equivalent to written as an equation? And don't be tempted to say, okay, it's strictly less than or, forget that, this is a primary notion. I know we pronounce it as less than or equal to. It's not a disjunction, it's just a, let's say, compares to. I could call it compares to. Any ideas? Yes? B, you said? Yes. So I will just flip the order of what you said. I said A join B. That's what you said? Equals B. Do we like this idea? So like, if I tell you A join B is equal B, and the other guy doesn't know about MITs, essentially they're thinking of this relation, these things end up being equivalent. This is like a theorem, okay? Prove it. This should be pink. And somebody else could choose this, and would also be correct. Okay. And what about, okay, so what I'm reaching here is that on one hand, I can have a poset with guarantees, some guarantees, which guarantees, like warranties, I don't know how you wanted to say it. Let's say binary joins, binary mates, tops and bottoms. And on the other hand, I could say, let's do algebra. Forget, I don't want to know anything about orders. Let's consider an algebraic structure that has two operations called mysteriously meet and join, two constants called bottom and top, such that a bunch of equations hold. And these equations will not be random. I'm like actually influenced by, let's say, what Panos said. Like one thing would be, okay, give me like algebraic properties you think join and meet would have. I think you will guess pretty much anything and there will be only one left. That's kind of tricky to guess. Yes?
It's symmetric.
How do we call symmetric in algebra?
Commutative.
Yes, and I found out how we say this in Greek. It's interesting, is it not? Commutative, we say it's a? Yes, unless you are in high school, you call it αντιμεταθετική. Weird, isn't it? Like, when you grow up, you realize that was the wrong name. It should be called μεταθετική. Anyway, so yeah, makes sense. This should be equal to that. And the same for meet. So this should be commutative as well. Come on, other suggestions? Yes? Yes?
The bottom and
What about the bottom?
alpha join bottom equals
Alpha join bottom equals?
τι έχουν πει. Alpha.
Okay, correct. What about this? Bottom, okay. How do you call this algebraic? We want to attract algebraics. It's the identity of no, bottom is the identity of join, okay. How do we call this?
The zero element.
Maybe it's called like that.
Null element, neutral.
Absorb something. like something.
Annihilator.
Yes, it also has this name sometimes. Like it sucks everything, right? Okay, what about top? Εκμηδενιστής. Wow, okay. Brutal. A join top. That would be top. Okay, so give me some more algebraic things. Yes?
Reflexive.
These are not algebraic, these are relational. Reflexivity, transitivity, antisymmetric. We are operations, yes?
A join A and A meet A are both A.
Well, what?
A join A and A.
Very nice. How do we call this? Does anybody knows? In Greek, I don't know. Idempotent. How do you? It's when you have like x squared equals x. Does it have? Do you know the Greek name? Αυτοδύναμο. Yeah, if you translate like that, it sounds like that. But have you heard this word αυτοδύναμο? Okay, idempotent. Okay, but so far you will agree with me it's algebra because everything is like operations, equations. What about associativity? Why nobody cares about this? This is the most essential one. Okay, because associativity gives me the right to say, give me an inhabited list of things and I will join them. You don't need to tell me in which order I have to do the joinings, okay? And even better, since I have an identity, I don't even need to require that the list is inhabited. Give me even the empty list, I will join it because I will return the identity of the operation. And even better, although in mathematics it's not so common to talk about bags or multisets, it means that I don't even care on the order you will write them because I have commutativity as well. So give me like a bag of things. You can have the difference between a bag and a set is that I can have multiple times the same thing. It doesn't have an order, right? But give me like some A's, I don't know, 3 A's, B and C, and a couple of C's. Tell me to join them, I'll join them. I don't need to know in which order you wrote them. I don't need to know where to group the parentheses. I have associativity, commutativity, and identity. So any bag of things, I can join it. And same for meets. First, so far, I'm not done with algebraic definition of what I'm defining. I'm trying to okay, it won't. I'm not done. There's something missing, and I want to get to alert something in case you haven't noticed it. Every time you study an algebraic structure, and it has like at least 2 binary operations, or at least two worlds, like the first example that should come to mind is a ring, which is actually an algebraic structure, and maybe you like it like that, but as you know in this course, we don't like it like that. I need to have the unary minus, I need to have 0 and 1, and now it is indeed an algebraic structure, thank you, with its equations. And if I know what a monoid is and what a group is, I can summarize this definition by saying like the orange part, which is the additive part, is an abelian group, and the blue part, which is like the multiplicative part, is a monoid. So if somebody knows what an abelian group is and what a monoid is, you can pretty much tell them, the ring is something that with these things is a monoid and with the other things is a group, an abelian group. But you could be forgetting something, and this is a crucial part. So every time you have an algebraic structure that has 2 worlds, 2 main operations, if you list actions for one world and actions for the other, and you're done with it, it's a useless theory because you could study them separately. If a ring was just this, take what abelian group theory has to offer about its additive part and what monoid theory has to offer about the multiplicative part, and you're done. But it's not like that. There's something always that connects the 2 worlds. Distributivity, and you have like 2 distributivities, the binary and the zero array. We discussed the zero array, but one is enough because you get the other as a theorem. So the zero array was the 0 times x is equal to 0. This is like 0 distributivity, so this is another name for this. For this. But so I have distributivity in a ring, and this means that ring theory makes sense as a theory to study it. Okay, I have something that connects the 2 worlds. So far I have nothing that connects this. Okay, what should be like the two worlds here? I want to place the operation together with its identity. So like it would be like the mid together with the join, the top, and the join together with the bottom. Okay, so so far I don't have something like that. I have associativity, commutativity, idempotency. Can somebody guess like a normal law that I would like to stipulate that combines the two worlds? Yes?
The meet and join of the bottom to the top.
The meet and join of the?
Of bottom with top and...
This, okay. It means something like that. For example, this would be a theorem. This will end up being always true because it's a special case of A join true, right? Okay. Again, I had like this little fight with Manolis here of whether, when you are given a definition, you want to strive for the most economical one, and we don't. We want to capture the idea. So maybe what you're saying would be very essential. It's not really essential to place it in a definition, but the actions I'm giving will not be like some of them. You could say, wait, these I can prove from the others, and I will give you an exercise to do it. But like I want to give them as axioms, as laws, because they capture well the behavior that I want to capture. It doesn't mean that they are not interprovable, but there's definitely one missing. Okay, one that has to do with combining these two worlds. Can somebody have a suggestion? Yes?
I think it's still distributivity.
Okay, your suggestion was distributivity. Any yes? What do you mean by that? No, wait. You are like in the next step. The first step is let's agree what the objects of interest are. And so far we are not done because we still have laws that they need to satisfy. Once I'm done with the objects, I need to say what are the means of transportation. Okay. So we have 2 votes for distributivity, and it's not. I will have a law that combines join and meet, and these structures will end up being called lattices, if you have heard this name. But like lattices in which distributivity holds will be special lattices, and we'll call them distributive in the same exact sense that I don't put commutativity in a group, and groups that happen to be commutative, they are special, and we call them commutative groups or abelian groups. So I'm trying to tell you that the algebraic structure that corresponds to the things I'm doing here and to this order theoretic perspective is not necessarily, these 2 operations don't not necessarily distribute over the other. In case they do, we call this thing distributive. Okay? The intuition, a good example, a good model to have in mind to infer what the thing is to think of join and meet like and or like union intersection, and see if you can infer something about doing something silly like taking A, joining it with B, and then intersecting it with A. This will give me the answer to what I want, and unfortunately, these are called absorption laws. So if you call the other thing absorbative or whatever, pick a different name. So what do you think this should be? First of all, it connects the 2 worlds, this equation. Okay, so I'm in the right track. And it's not going to be distributivity. Yes, Rafael? Okay, good. Okay, this is join.
Okay, sorry. A meet, join, the join of A and B.
You're complicating things too much. Think of... What's that? I think you have a better answer for this. No, yeah, it's just A. Isn't this just A? I mean, you get A, you make it bigger possibly by joining something of B, and then you intersect it with A, so any possible extra things that you got, you throw them away again. You didn't do much. So this is like one of the absorption laws, and you can guess that, this is equal to A. And similarly, you can guess that if I first meet with B, let me see what I need to write here. I think I need to write this, and then I join with A. Yes, this should be A. And is there something else missing here? I think these are enough, but I'm wondering. Okay, yeah, the rest is inferable. Okay, so I'm done now. I have defined an algebraic structure. It's called a lattice, okay? It has like all those things and like these things. Some people call them bounded lattices, and when they don't have these things, they just call them lattices. It's like a matter of nomenclature if you want to always have a top and bottom or not. Or sometimes they are called 0-1 lattices, 0-1 or bottom top lattices. If they have these things, it's not really essential. And one thing to realize about this structure is that all the laws that I have are like symmetric in join and meet. This does not happen in, I have like two binary operations, and they are treated like with the same respect inside the world of a lattice. This does not happen in a ring, for example, or in a field or whatever. They are different. So this gives rise to a duality principle in lattices. Essentially, when you prove something, you gain a theorem for free. Like swapping all joins for meets and tops for bottoms, you will end up it's like a 50% discount on the theorems you will have to prove. Now, this thing goes both ways. So if I start with a lattice, I can define this order. I can define it like this way, right? Define this to mean that. And if I am in a poset that guarantees existence of joins and meets, binary, and has a top and a bottom, I can define these operations. So we are discovering that, let's call them order theoretic lattices. This means posets that have binary joins, binary meets, bottom and top, correspond to algebraic lattices, which is this structure that I defined there, which is they have two binary operations, two zero operations, and all these equations that I gave you. And you can study do normal algebraic stuff that you want to do. You want to define what is a... Okay, now it's the term, Areti's term, because I haven't said yet what it means to go from a lattice to a lattice. So what does it mean to go from an algebraic lattice to an algebraic lattice? Let's look at the protagonists and figure out what the correct notion of transportation would be. Oops, sorry. So if you see here, I have these are rings. Forget rings. So if you look here, I have 4 protagonists, all of them operations. I know what it means to respect operations, right? Of any arity. And boom, that's it. So a transportation from a lattice to a different lattice will be respect the structure of L. And what is the structure of L? Respect joins, respect meets, respect bottom, respects top. 4 things, okay? So if I have all those 4 things, I have what is called the lattice homomorphism, which is a means of transportation of going from a lattice to another. And since most of you have taken some algebra here, it makes sense maybe to say what the equivalent things would be like. Okay, I take it for free what a sublattice means, in the same sense that I take it for free what a lattice homomorphism means. Homomorphism means respects all the operations. Sub-thingy means it's closed under all, it's a subset that is closed under all operations. And be careful here, I have constants. What does it mean to be closed under a constant? Yes? Yes, that the constant is inside, right? Okay, so I have this idea of a sub-lattice. I know what it means, I know what the homomorphisms are. what do I want to do with this? Okay, so I know the arrows. I think I have a picture of what, of how the world looks like. Okay, I know what I'm studying. So, in algebra, like whether you were doing ring theory or you were doing group theory, eventually you studied something called like homomorphism theorems or something like that. Essentially, they try to characterize some homomorphisms and properties out of them of looking at what happens like if of looking at the kernel of something, and the idea would be like what would the kernel of phi be here from the intuition that you have from group theory and ring theory. There should be like a conflict of maybe interest here, like what would be the kernel of an homomorphism here. I want suggestions.
All the elements that go to the bottom.
To look, okay, so you would define that the kernel of phi would be all the pretty much the pre-image, right, of bottom. Maybe you like to put singleton here, I don't know. Okay, why? Because here it looks like 0 bottom. So let's see the pre-image of that. And hopefully what happens in group theory and ring theory is that you look at this pre-image and you find out that this kernel has some very nice properties as a subset of the domain. Right? I mean, I know it's ideal, it's a normal group, it's whatever, it's good. Okay, it's not just a subset, it's a good subset.
An ideal subset.
It's an ideal subset, okay. And, okay, but does somebody have want to pick a fight with Sotiris? Would be nice. Sotiris can also pick a fight with Sotiris. Manolis, yes?
I mean, we're kind of singling out one of the two.
Bottom, yes. Sotiris has made it clear since the beginning. He likes bottom, okay? Yeah. But one would say, okay, in a ring, just a second, in a ring, the two things, 0 and 1, like you have two constants there, they are not, they have a reason to single out 0. Because it's different. It has more properties or whatever.
Whereas here it's a bit symmetric, so you can include both.
You're breaking the symmetry.
Both, no. I mean, you take as a kernel something that goes to either of them. That would be weird. What I was trying to get to was like you have two choices of a kernel, let's say. Like, look, okay, so you have a lattice here and a lattice there. Both I consider them with 0, 1, with top and bottom. Look like all the subset, which are all those guys that went to top, and try to figure out if it has some nice properties. Look at all these that went there. Obviously, these things are disjoint, right? Because phi is a function, cannot send someone unless the lattice on the right is one element in which top is equal to the bottom. I'm not prohibiting this, and I would not even be allowed to prohibit this if I want to still stay within algebra, because the only way to prohibit this was to say something that is not an equation. It's the exact opposite thing of an equation. Okay, so I have not done that. There are lattices that the single point lattice is a lattice. However, I don't have an empty lattice. Why? Top is an element. Okay. If I understand that lattice means this, I do have an empty lattice. Okay. If I understand that lattice is a bounded lattice or a top-bottom lattice, 0, 1 lattice, then there are not empty such things. But since I'm talking about empty things, just a reminder: are there the world of posets? In the world of posets, do I have an empty poset, or is there a reason that prohibits the yes?
If we're just talking about the set of the relation, then there is.
That's what a poset is, okay? And if I look at the axioms, no axiom, all axioms are compatible with an empty set and the empty relation. So there is an empty poset because the empty relation in it satisfies trivially all those things that it has to satisfy. Okay, so a good exercise here is like to figure out good properties that these candidates for kernels have, and we will end up with this reaching the idea of what an ideal is in the order theoretic sense, and compare this with the algebraic sense, and like understand better what's up with ideals and the dual notion. Every notion that we define in a lattice or in a category, as soon as we get to categories, also comes for free, also discount, with a dual concept. So we figure a nice idea, a nice concept, I don't know, and we gain for free a new idea, which is like the dual concept of that, in a very systematic way. We don't need to think about it. Questions so far? Yes?
The fact that we now have two choices for what we consider a kernel kind of got me thinking, why don't we consider the pretty much of one a kernel in ring theory?
Okay. First off,
This is a question.
it's not so irrelevant. I don't know if this is taught I think I graduated without listening to it at all. It's like, what is the kernel of any function? Has anyone seen that? Like, you have a function from A to B. Actually, the word kernel is like way more general than algebraic structure. Pick A and B, I don't care if they are sets or types, whatever. You have a function from A to B. The kernel of F is defined. Has anybody seen this? Okay, it's defined to be a very specific relation. It's the one that consider things on A to be equivalent if their images are the same. So let's write it down. First of all, what is the type of curve? It's a relation on A. And let's remember, this means that it takes two A's and it becomes a prop. And I have to say which relation is. So, like, X is related with this, with epsilon, means, help me here. Okay, yes, they have the same image. You need to verify that this is indeed an equivalence relation. And once it is an equivalence relation, hopefully you know that any equivalence relation gives rise to a partition of something, and you can take the quotient of it. So you can either see this as an equivalence relation or as the quotient from that relation. And this is exactly pretty much what happens in... you have a tight... These are the things that annoy me with nomenclatures. You have like a small class here between what in group theory is called kernel and this idea of a kernel. Because if I stick with this idea to the kernel, what is the kernel for a group? If you have an homomorphism, you would think the way you're normally taught, like that kernel is everything that goes here. But you know, if you've studied group theory, that as soon as you do that, as soon as you have a homomorphism, and whether you want it or not, your whole group here gets arranged in a pretty way, gets arranged like that. Here you will have also three elements, whether you want it or not, and here also three elements, and it looks like that. Possibly you can have some things lying around here. Okay? And you have some theorems of group theory that say that certain things have certain good properties, but in the sense that I'm saying, I'm defining kernel here, the kernel is not this subset. The kernel is the relation that says that these things are equivalent and these are equivalent, blah, blah. And it's like you pick your favorite candidate representative there and you say that, okay, the kernel is this guy. While the kernel of phi technically would be the equivalence relation whose quotient are the orange guys. Okay, does that make some sense? So just to come back to your question, you have a kernel anytime you have a function, right? So the reason you focus there is because you want to end up with the right notion of good sub thingy, and subring is not always so good. So you end up studying ideals, and the ideals would be this, and the kernels are ideals. So like in the same way that in group theory you have like normal subgroup and kernel are like two sides of the same coin. If you have a normal subgroup, you have a homomorphism whose kernel is the normal subgroup. And if you have a kernel, you can look at this thing and it will end up being a normal subgroup. This is the similar relation to the ideals in ring theory, and more interest to us in order theory, a similar relation to a concept that I want you to discover. It's called the ideal, but like don't look it up. Okay, discover it. What happens if I take the pre-image of the bottom, and a dual concept that will be if I take the pre-image of the top. So if you look at these things, these designs here, they are like nice. They don't look nice at all, but like if you design them nicely, they will be nice. Okay, and the idea is that they correspond to dual concepts in order theory, and a big homework would be trying to investigate these properties that are nice if you look at the pre-image of bottom and the pre-image of top. You could, and I want to argue that you could come up with these nice subsets independently. So it's really nice if you have various ways to say, okay, let's look at this thing. I learned in group theory this thing. Let's try to do this in a lattice. You will discover this concept. You could start like, let's see what happens if I take a subset that is closed under some things that has some properties. And you end up like with the same concept, and then you kind of are more confident that you are approaching an interesting idea. Yes? Wait. Okay, so it's a question or is it an answer? It's a question. Okay, go ahead.
Άμα το ορίσουμε αυτό σαν σχέση ισοδυναμίας, προκαλεί μια διαμέριση.
Whether you like it or not. So you're talking about this one?
Όχι, μιλάω ότι εφόσον έχουμε το K του F σαν σχέση ισοδυναμίας, τότε αυτά τα στοιχεία που καταλήγουν στο 0 είναι ένα στοιχείο της διαμέρισης.
Yes. So, first of all, whether you like it or not, as soon as you have an equivalence relation, there corresponds a partition, and as soon as you have a partition, there corresponds an equivalence relation. These are like two sides of the same coin. Wait. The image I drew here, I drew it thinking of groups, and this is why it has some extra properties. The extra properties I have here are like that there are 3, and 3, and 3. This is group theory. But in a more general setting, I should not do that. I mean, because here I'm trying to convince my knowledge that kernel makes sense for any function between any set to any set, and it has to do with what you're saying as well. So actually, it should be something like you have maybe all these guys are sent here, and this guy only here. This cannot happen in a group, okay? But I don't care about groups right now. And these two guys sent there, and I have a bunch of other guys here that are not the image of anything. This function, which is drawn in a very ugly way, it determines a kernel, an equivalence relation, and will be the equivalence relation that corresponds to this equivalent classes. Okay. Any other questions? No. Okay. So I think I have what I want to have for the time being on order theory. I just want to give you a warning on things we write, because usually when you say lattice and stuff like that, they start with a poset, and as I said, sometimes I don't want to insist on antisymmetry, so I may have like prosets, and I will abuse the notation and the nomenclature. I might call it a lattice if it has all these nice properties of a lattice, except possibly this antisymmetry. And the idea is that some things work kind of better than having to worry about antisymmetry. I can have like comparable elements like that, and whenever I want to go to a lattice, I will do the construction that Manolis promised to send on Zulip and never sent it, which pretty much says like collapse these kind of things, call them a new point. Okay, it's a relatively simple construction to do. You've done similar things here when you define exactly what is the group divided by what? By phi, I could say, or by kernel of phi, okay? Which ends up being these things that we want. So like maybe when I say lattice, I will not always have this the antisymmetry, and I want to come back to close this with a quiz question. Like you would see this definition in the best common divisor. You would not see it as a best, but I will call it best. Now I need to change the G, but I will not change it. GCD stands for best common divisor. And it has these two properties. It's a common divisor, and among all common divisors, it's the best one. We've seen this so far. And then we write at the end of the definition, this is something I forgot to say the other time, the previous class, we write M is equal to, and we give it a name. Maybe you want to call it like GCD of A and B. When you are studying number theory, you use this all the time, that you even consider this implicit. You just write parentheses A and B, and this is the greatest common divisor. And now my quiz question, to end the class with this question, is what kind of prop is this one? And the kind of props, remember, or the race, I was saying this metaphor when we were killing monsters, we were too young back then, like it's these things. So, it's a trick question, yes? It tries to fool us, okay? It tries to fool us because it looks like an equality sign, but the only correct way to interpret this equality sign is as if it's some kind of weird notation. So I tend to write in green the things I'm defining. So like, it's a ternary relation, okay? Oops, sorry. Look what's green here. I don't know if you can see it, but it's these, and these are green. And it's a ternary relation because it has these three arguments. And it's important to realize that it's not an actual inequality, because I will want to use it and I will want to prove it various times. And I think the difficulty when you are like either teaching or trying to understand number theory, sometimes you have things like you want to prove that something greatest common divisor. It doesn't look like so easy because you think that this is an equality. And you're trying to calculate this and prove that this thing is equal to that. It doesn't really work like that. If you want to prove this, translate it to the thing it is, it's a conjunction, and just prove these two things, and this is always the correct way to go. And if you want, and then you have some further notation, something like when you call something like that, what you are really saying here is that I'm hiding the greatest common divisor here. Right? Now it looks like a relation. When you want to prove that, essentially you want to prove that the set of common divisors of A and B is the same as the set of common divisors of C and D, and you don't see this as like an operation. And exactly the same thing happens in calculus when you define limits and you say that L is equal to the limit, I don't know how you want to go to denote this, like, this is not an equality. This is what? What's the race of this thing? AN is a sequence. Essentially, I'm checking if you remember the yes? No. There is one like a hidden implication probably somewhere. But like the kind or the race, like the outermost proposition. You would say what?
Universal quantification?
It's a for all. It's like for all.
Epsilon.
It's always epsilon, right? For epsilon, there exists something, but I'm already inside the stomach of the for all monster. It's a for all thing. And it looks like an equation. But usually we take care of this to... Okay, so what is the problem with that? The problem with that is that you could say like A equals B, and then B equals C, and you want to say therefore A is equal to C. But you don't get this for free, just because you are using a notation that uses this symbol. So if you want these things, you need to prove them. And usually when you use these kind of notations, we do have at least uniqueness, even though we don't have existence. So this thing may not even be defined. So how can you tell me that two things are equal if on the right-hand side, it's not even defined? It doesn't make sense. Okay? And the worst case happens when you have something like, you don't even have uniqueness. This happens in notation like complexity notation, that you say that F is equal to O of N or something like that. And it's a terrible notation in this sense, because you cannot even justify half of the things you want for the equation, for the quality. Okay, so we end here, and next time probably we start see what we need to add to all this point of view to start talking about categories. Okay, so till Friday, and earlier than that till Zulip.